All right, welcome to section 3.4a. We are beginning our discussion about linear programming. Our learning target today is to solve programs using this process called linear programming. Some essential vocabulary. Linear programming is a method for finding a minimum or maximum value of some quantity given a set of constraints. The constraints form a system of inequalities and form what's called the feasible region, which is all the values that satisfy the constraints. So we've been doing the initial part of this process already. We have been looking at a set of constraints. That's our system of inequalities. And then where they overlap, that solution region is called the feasible region. That's the area where all of the inequalities work. So we're going to be looking for our answers within that region. The quantity that we're trying to maximize or minimize is called the objective function. Often this quantity models cost or profit. So businesses would use this model if they were trying to maximize their profit or minimize their costs. It says, with the following constraints, find the maximum and minimum of the objective function c equals 2x plus y. Your objective function is not graphed. We graph the constraints, and we're going to use that graph to help us figure out what values to plug into this objective function. All right, so our first inequality is x is greater than or equal to 2. So we are going to have a vertical line at 2. It will be solid since there's an equal sign. And it is going to be important that we graph this fairly accurately so that we can really find that feasible region. And then we are going to shade to the right of that. We want x's to be greater than or equal to this value. So we're shading all of this section. All right, our second inequality says y has to be greater than or equal to 3. And I'm actually going to combine these because the first one is saying that y has to be greater than or equal to 3, but we also want y to be less than or equal to 6. So the result of that is that we have two cutoffs, one at 3 and one at 6. We want to be greater than or equal to 3, so we want to be going up from there, but we also want to be going underneath the 6. So the net result of that is just the section in between those two lines. And then our third inequality says x plus y is less than or equal to 10. If we graphed it with intercepts, putting a 0 in for each one of our variables one at a time, we would get 10 for the other variable. So this is a nice, easy way to get this graph done. If you want, you can solve this for y instead by subtracting the x to the other side. You're still going to get the same line. We are starting here at 10 for our y-intercept, and we're doing a slope that's -1. All right, another solid line for that one. And this time we want to be underneath that line. So the section of our graph where all of the constraints are correct, are being satisfied, forms what we call that feasible region. All right, so let's go through this. We want it to be in between our two green lines. We want it to be to the right of our blue line, and we want it to be under our red line. So this section in here is what's creating that feasible region. So when you do your graphs, I would recommend using a straight edge so that you really get an accurate line, because what we're going to be looking for is is the corners of our graph. All right, let's get a line in here. My board's being a little funky. All right. All right, so the step 3 now is to find the coordinates of the vertex. We want to find the corners of this feasible region. And we're going to list those in our chart, because the last step then to this process is to evaluate each of those vertices using the objective function that they gave us. So my first vertex right here, we are at the coordinates 2, 3. And it doesn't matter which order you go around for your vertices. I'm just going to keep going this direction. So I have the point 2, 6. This next one here is hitting at, it looks like 4, 6. And my last point here would be at 7, 3. All right, so we have all 4 of our vertices, and now we're going to evaluate our objective function. And that objective function we were given, one second here while I adjust my board again. Our objective function was c equals 2x plus y. So we're going to plug each of those coordinates in and see what we get for our maximum and minimum values. All right. So for the first one, c equals 2 times x plus our y value. Our x was 2 and our y was 3. I'm going to go ahead and set these all up. C equals 2 times our x plus our y, 2 times our x plus our y value. And then let's look at what we get for each of those values. The first one, 2 times 2 is 4, plus 3 we would have 7. Our second one, 2 times 2 is 4, plus 6 gets us 10. Our third one, 2 times 4 is 8, plus 6 is 14. And our last point here, 2 times 7 is 14, plus 3 is 17. And they asked us to find both the maximum and the minimum. So right here is my lowest value, and right here is my highest. So I would say I have a minimum of 7 at the point 2, 3. I have a maximum of 17, and that occurred at the coordinates 7, 3. So once again, our steps. Our first step is to graph all of our constraints, draw our picture, be very accurate with your lines. Step 2 is then to shade in where they all overlap. Step 3 is to find the coordinates of each of the vertices. And step 4 then is to evaluate each vertex using that objective function. All right, let's try another example. This time our objective function is c equals 3x minus y. We don't have to graph that, remember. We just are going to use that when we do our final looking for our maxes and mins. So step 1 was to graph our inequalities. You will often see constraints that include these two inequalities. X being greater than or equal to 0 means we are here going this direction. Y being greater than or equal to 0 means we are here and we're going up. So these two combined really just says we need to be in quadrant 1. And if you label that you know that you're in quadrant 1, we're not going to bother shading all of this because it just gets kind of messy. All right, let's go ahead and graph our first slanted inequality here. We have y is less than or equal to negative 1/2 x plus 4. So we are going to start at 4, and we're going to do a slope of negative 1/2. Again, we want to be as exact as possible. So go ahead and use a straight edge and put your line in there. All right, so we have our green line. We want y to be less than or equal to that. So we are shading underneath it. And then our next one, y is less than or equal to negative 2x plus 10. So we're going to start up here at 10 and have a negative 2 slope. We're going to draw a line in again. I got to re-angle my line here. All right, and this time we want to be less than that, so underneath. So once again, we need to be in quadrant 1, so we're up above those blue lines. And we need to be underneath the green and the red. So let's go ahead and darken in our feasible region. We have to be under the green, under the red, but above and to the right of the blue. All right, so that is our feasible region. Step 3 then is to find all of the different vertices of that region. So our first one is 0, 0. Our next one would be this point, 0, 4. And notice that not every point that we plotted to get our lines drawn will actually be a vertex that we're going to use. We just want the ones that are the boundary of our feasible region. In other words, that point at 0, 10 is not going to be included. We need that point, so the coordinates would be 4, 2. And our last point here is 5, 0. Now, in these two examples, we've had 4 vertices for both. You won't always have that situation. You could have more or less. Just depends on the shape of your feasible region. All right, let's evaluate our objective function. We want 3 times x minus y. So 3 times 0 minus 0 just gets us a total of 0. For our next point, we have 3 times 0 minus 4. So we have 0 minus 4 is negative 4. Our next point, using the vertex 4, 2, we have 3 times 4 minus 2. So 12 minus 2 would be 10. And our last one, we have 3 times 5 minus 0. So we get 15. All right, so our maximum would be this 15. Our minimum would be this negative 4. So again, we would summarize the answer to our question here and say that we have a minimum of negative 4 at the coordinates 0, 4. Okay, that gave us a minimum. We have a maximum of 15, and that happened at coordinates 5, 0. So we are just today practicing how we actually create the feasible region, how we find the vertices, and how we evaluate the objective function. Tomorrow we will move into the whole process of now looking at what does all of this mean and how are those constraints figured out. All right, let's try one more. This time it says our objective function is 4x plus y. We are given some constraints again. This time we want x to be greater than or equal to 1. So we are going to have a vertical line at 1. And we want to shade to the right of that. We are going to have the inequality y is greater than or equal to 2. So horizontal line at 2. And we want to be greater than, so shading above. I'm going to give you guys a minute. Go ahead and pause the video and try graphing the next two inequalities on your own. All right, let's check how you did. Y has to be less than or equal to negative 2x plus 7. So we are going to start on the y-axis at 7. And we need a slope of negative 2. We're going to draw our line. And we want to be less than that, so we would be shading underneath that line. Our last part, our last constraint, we are starting at 1 on the y-axis, and we want a slope of 2. And let's draw the line in. And this time it says that we want to be less than that. So we are underneath that one. So our feasible region, we have to be above green to the right of blue. So above green to the right of blue, under the purple, and under the red. So we have this little section right in here. That's our feasible region. All right, we need to figure out our coordinates of that. This one's going to be a little harder just because we are hitting at some points in the middle of a grid on our graph here. Let's start with this point. We have coordinates 1, 2. Our next corner would be this one, so coordinates 1, 3. My board's not cooperating again. There we go. All right, so we said 1, 3. Now, this point, it appears to be about 1.5 for the x coordinate here and 4 for the y coordinate. We do want to make sure and check that. And that is where the green and the red lines are intersecting. That means it should work in these two inequalities. So let's check. If we put 1.5 in for x, 2 times 1.5 is 3, so we get negative 3 plus the 7 would be 4, which is what we're supposed to be getting here for our y value. If we put a 1.5 in for x here, 2 times 1.5 is 3, plus the 1 gets us 4. So the point is working in both of those. We've found it correctly. This one here appears to have coordinates at about 2.5 for x and 2 for y. Again, let's look at which two inequalities are intersecting for that vertex, and it looks to be green and red. Now green we know has to be at 2 if it's on that line. So we said coordinates were 2.5 for x and 2 for y. So it fits our green line that that y is equal to 2, and we also want it to fit in the red one. So if we have a y coordinate of 2, does it equal -2 times our x coordinate plus 7? Well, -2 times 2.5 is -5. -5 plus 7 does give us a 2. So it does fit both the green and the red inequalities. So we have our 4 vertices. We now have to evaluate them in our objective function. So 4 times our x coordinate plus our y value. We get 4 plus 2 would be 6. Our second vertex, plugging it into our objective function. 4 times 1 plus our y value of 3 gets us 7. 4 times our x coordinate, 1.5, plus our y value. Well, 4 times 1.5 would be 6. 6 plus 4 would give us 10. And our last point, 4 times 2.5 plus our y coordinate. So 4 times 2.5 would be 10, plus 2 would give us 12. So we would say we have a minimum of 6 at the coordinates 1, 2, and we have a maximum of 12 at the coordinates 2.5, 2. All right, so once again, you are graphing all of your constraints, all of those inequalities, finding where they all overlap, your feasible region, finding the coordinates of each vertex of that region, and then plugging those vertices into your objective function to find your max and min. All right, so go ahead and practice this with worksheet 3.4a.